So hello again. Tonight we're going to talk about doing continuous satellite surveillance of solar system bodies other than Earth, but we'll discuss that we do that uh, on Earth already. So if you haven't been paying attention, on March 11th, the Minor Planet Center, the MPC, these are the folks that monitor comets and asteroids and moons and such, they made a release, 2025-E155, where they confirmed that Saturn now has 274 moons. Earth has one. Saturn has 274 moons, which makes it more moons than any other body in the solar system. Jupiter, in case you're curious, currently has 95 recognized moons. So the numbers keep going up the more we look. The idea is that maybe before humans came to be on this planet and before we started counting moons of Saturn, there were a bunch of even larger moons in orbit around Saturn, and they collided, producing debris, leading to this increase in moon count, but most of it was so small that we can't see it from Earth. 63 of Saturn's moons have formally recognized cataloged names. Some of them are large enough to see from Earth. Some of them are large enough that can be seen through amateur telescopes. Of the newest 128, only one has a formal name, a mythological name. The rest of them are uncatalogued placeholders, S/2009 S1. It was first observed in 2009, a moon of Saturn. So within the number of cycles over a year, it's the first in that cycle. But if you want to know the sizes, the largest moon of Saturn is Titan, and it's about 3,227 miles in diameter. The smallest of these inclusive new moons is 980 feet in diameter. For reference, the moon is 2,159 miles in diameter. The moon is around half-ish the size of Titan. But there are a lot of objects in Saturn's rings that are on par with the S2009 S1, the difference being they're in the ring and they're not considered actual moons, and they're not even like dwarf planets because they don't orbit the sun, they aren't big enough to be round, and because they're in the ring system, they haven't cleared out their orbital path. So they're part of the ring, but they're not moons. They're moonlets, but not moons. So of these new moons, most of them have irregular orbits, and there's a grouping of orbiting moons around Saturn for each category and location. And these fall into the Mendel-Fari grouping, and they have chaotic properties. Now, the properties are their orbital behaviors. Some of them are small enough, they're not big enough to be round. They don't have hydrostatic equilibrium. They're oddball or potato shaped, which would lead some of them to be not solid moons, but just rubble piles held together by static electricity and gravity. Some of them were almost kicked out of Saturn's orbit. They have very elongated non-circular orbits, so it takes a while for their orbit to go around Saturn. Some of them have tilted orbits. They're in orbit around Saturn, but instead of being around the equator of Saturn, like they would be if they fell into a regular group, they're tilted. For reference, the Earth's moon is tilted 5.145 degrees to the ecliptic of the solar system. And even the Earth itself is tilted 23.44 degrees, which is why we have seasons. Some of these new moons of Saturn do not orbit in the same direction as the planet rotates. They are what is known as retrograde orbits. And there's a whole class of moons that do exhibit retrograde orbital behavior. They're called Norse moons. Some of them have different axial rotation. So if you think that, let's say Saturn is rotating counterclockwise, some of these moons may be orbiting clockwise. And some of them don't just spin in one direction. They have multiple rotation vectors. So they're wobbly, which means how long is a day on one of those moons? Well, it varies which direction your orbit's going. But all these indications are chaos due to collisions and captures. Large pile of junk, but not together, just like scattered. So are these really new moons, or are they just simply unobserved moons? Of the 274 total moons that Saturn now has recognized, 4 of them are easily visible in binoculars or small telescopes. An additional 2 of them are visible using larger amateur telescopes up to around 10 inches, 254 millimeter. The 4 largest visible moons, the next 4 up, are only visible using large Earth-based or space-based telescopes because of atmospheric distortion. 136 of these smaller moons were observed using probes that flew by. They were on their way to somewhere else or to go into orbit around Saturn, and so they saw them. But since there's no other probes in the area and no other science teams looking for them, they're in the queue waiting to be confirmed. This latest 128 were confirmed by the Canada, France, Hawaii telescope near Mauna Loa, and they used adaptive optics. So it was actually confirmed by telescopes on the Earth's surface from things that were first observed out in space by space probes. From the perspective of human existence on Earth, these new moons are not really new. They've been around for a long time. Maybe we observed them, but they weren't confirmed yet. But now we have confirmed a chunk of them. New does not mean new for Saturn. They could have been in orbit around Saturn for billions of years, but they're new for us, and new if we just observed and confirmed them. If you state it officially in a press release as newly discovered, that's not sensational enough. So they'll just say new moons of Saturn, but they're not really new. So if you want to know why they come out in clumps like 128, nothing special about 128. It just happens to be how many they had in the queue that got confirmed. Not a magical, due to it being a power of two kind of thing. But the reason why this happens in clumps is there'll be a queue of, look at what we saw, and then now we got to confirm that. But it's got to be confirmed by other instruments or other teams of scientists that are doing the observing to compare notes. So for example, when the Galileo probe orbited the planet Jupiter, it observed many new moons of Jupiter, which stayed in the to be confirmed list until the Cassini probe was on its way to Saturn and passed by Jupiter. And since it had nothing better to do, they moved the spacecraft around. So on its flyby of Jupiter, Cassini could confirm a number of the new moons of Jupiter. Cassini observed in its orbits around Saturn a bunch of new moons, and they could not be confirmed by the Hubble Space Telescope or the James Webb Space Telescope. It's a matter of size, the albedo, the reflectivity of them, and the angles. Like, can we get it to point that way? Remember that HST is orbiting the Earth. So as the Earth goes around the sun, Saturn may not be close enough for several years for it to be able to see Saturn well. Same with the James Webb Space Telescope. It is not in orbit around the Earth. It is in orbit with the Earth around the sun. So until it's pointing towards Saturn, no ability to confirm any of these new moons. So what they did was say, well, the next time we send a probe to Saturn, we'll confirm them. But as it turns out, the next probe to Saturn is going to be a rotorcraft, a hovering helicopter that's designed to fly in the atmosphere of Titan. The probe is called Dragonfly, but it's not designed to be launched until 2028. And it won't. If we launch it in 2028, it won't arrive at Titan until 2034. Space is big. We're not that fast. And that's presuming that the funding continues until then and that there's no technical snags. So a lot of these new moon confirmations for Saturn were from the Canada, France, Hawaii telescope on Mauna Kea using adaptive optics. That's where they shine one or more bright yellowish looking lasers to the bottom of the atmosphere, and the beam gets distorted. So they pick up the distortions in the beam and they adjust the optics of the telescope in real time to accommodate that so they can get a much sharper image so they can see these smaller moons. So one reason we know a lot about the Earth is because we put things in orbit that look at the Earth on a near constant basis. And we have a number of different types of instruments operating in different spectra, like infrared, visible, ultraviolet, even X-ray. And they're in different orbits, low orbits, medium orbits, geostationary orbits, high or elliptical orbits, known as molnias, or polar orbiting. And we upgrade and replenish these on a regular basis because things go bad, things wear out. They get hit by micrometeoroids all the time. Or they, even if they're ion propulsion, they run out of fuel because when they get launched, That's the most fuel they'll ever had, and they're constantly using it. So as it runs out of fuel or something breaks, they have to either deorbit them successfully to not produce debris, or if they're geostationary, they'll put them into what is known as a parking orbit and just leave it there for, I don't know, a few hundred years. But the reason why they can afford to keep replenishing and expanding these constellations of Earth observing satellites is there'll be money in there. Communication satellites, monitoring crops, doing surveys for mining, doing construction planning, taking pictures of an area that, like, if you've ever seen the pictures from places like Brazil where they're clearing rainforests, you can see the rainforest clearing over time. Archaeology, they take pictures of dig sites using synthetic aperture radar. They'll take pictures through foliage, through the jungle, and see something underneath on the ground. They'll use synthetic aperture radar to see through water, so they can see submerged sites. It can see through Sahara desert sand, see things a few hundred meters down. It can even look through certain densities of rock, which allows them to see some of the early settlements that are buried beneath the sands in the Middle East. And then there's the national security satellites. We got to have them all always up there looking for optical stuff, infrared stuff, radio stuff. And then sometimes we actually put up things that are purely for the sake of science, like monitoring ocean sea levels and ocean currents and ocean temperatures. We know all that stuff because we've spent the money to be continuously observing Earth in all these various ways. But we just haven't done that elsewhere. So we know these things about the Earth because we observe it. Since we're observing it in near continuous real time, we can actually watch the formations of things, like going from normal weather to tropical storm weather to hurricanes, watching the hurricanes move and then dissipate and going back to a tropical weather again. You can watch the formation of tornadoes until they end. You can watch general weather movements, atmospheric troughs and things like that. Over time, you can watch climates change. You can watch wind movements. You can watch ocean currents like the Gulf Stream. You can track all of these natural and man-made disasters like fires and floods, insect infestations on crops. You can watch atmospheric movements. When there's something accidentally released into a river or the ocean, you can actually watch, usually in infrared, the chemical plumes that come out and see where it went to know how to, like, well, let's close the beaches here because that's going to be bad. If we didn't observe these things, then we might not know about something until it's too late and people might get affected by it. So that's why we do it. Of late, there's been a lot of, as I said, synthetic aperture radar observing of under the oceans, through dense jungles, basic sand, ground. We do observe. But when it comes to other things in the solar system, our observations are spotty at best or incomplete. When we have something orbiting something, we can take a look at it. Like, the moon has the Lunar Reconnaissance Orbiter that's been up there for a while. When it runs out of orbital correction fluid, it'll probably just be crashed into the moon. The Mars Reconnaissance Orbiter, same sort of thing. When it runs out of orbital correction fluid, propulsion fuel, it'll probably just be crashed into Mars. But in the meantime, they can only see below them as they go around. So if they want to see a particular spot over time to see, like, dust devils, well, as they're flying overhead on Mars, they want to see the dust devils. They can't just stare straight down because they're going in an orbit. They have to stare down and tilt and then assemble the frames together. That's why if you ever look at the dust devil videos, they look like they start out kind of looking almost as a side view, and then they go vertical, and then they go to a side view again. It's because there's only one probe taking the pictures. Or they can't send stuff back. So if they wanted to take images of the far side, the current as it rotates far side of Mars, you have to wait until the probe comes back around to send that data to Earth. So there's an orbital lag. Or we do what is known as polar stripe orbiting, where we'll put it into a polar orbit, and as the planet turns underneath it, they'll just take continuous photos as it orbits, and they make these stripes, and then they assemble the stripes together to create an entire planetary view. And since we're only putting one probe in orbit, how do we look at the poles if we're only viewing from the equator? We don't have any of these probes in what would be known as like a geostationary orbit equivalent for other planets. or they're staring at the same spot all the time, because having only one probe, you don't want to waste it just staring down at one spot. So they go orbiting. But if you had more of them, then you could put them around the equator of that planet, say Mars, and see what's going on all the time. If we had more satellites orbiting these other planets and moons, we could see more of what's going on. We would need multiple of them to cover the entire planet, because while we might have 3 orbiting satellites that can cover Earth, and then 3 ground stations that can look up to space, Earth is an okay size. But when you get to planets the size of Jupiter and Saturn, you're going to need more satellites. So if we want to watch, let's say, what's going on with the weather at Jupiter and Saturn, as a probe goes over the poles, we can take snapshots, because Jupiter and Saturn orbit relatively quickly for how big they are. So it's easy to get time-lapse photos. When you're talking about Uranus and Neptune, they're larger than the Earth, but rotating a little slower, so you can't get the same thing with just one satellite. But imagine if we could be orbiting one of the moons of Jupiter or Saturn that we suspect has a subsurface ocean, and instead of just doing a flyby snapshot and going, oh, look, I've seen like jets coming out of what would be a crack, you could actually have a probe that's staring down at where the cracks are and see them go from ice sheet to crack opening up to ejection and then closing back up. You get a complete picture of it. Imagine if you had something in orbit that could allow you to see the lava volcanoes of Io or the ice volcanoes of Enceladus. There's lots of stuff out there that we just, by luck, have the ability to have images of it, but we don't have any long-term cycle of from beginning to end. So here's what I'm recommending, just me, one guy on the internet. Why don't we start deploying similar constellations of varieties of satellites elsewhere in the solar system? You know, we don't have to put everything out there everywhere all at once. We can start with, like, I don't know, let's deploy equatorial orbiting geostationary or Saturn stationary or Jupiter stationary band of satellites. And we can watch things going on as it orbits. We'll be looking down and we're orbiting at the same speed the planet's rotating, so we can stare and watch how things change over time. Start with a small number of satellites, maybe not covering everything, like maybe missing the poles, but maybe just get the equator. Can't even get the upper and lower latitudes. If that worked for Earth, and it was very meaningful to do so, maybe we can start looking at the counterparts on these other planets and moons of weather and climate and archaeology, maybe. But much as we sent probes to the moon to orbit and land before we ever sent people there, we wanted to survey things. So we had a probe that landed on the moon, several of them, called Surveyor. And then we sent probes to Mars called Viking. But we also sent orbital and flyby probes because we needed the information to see if it made sense for us to go there and exactly where to go there. And if we want to do some of this natural resource mining elsewhere, then maybe it would be commercially viable to do some surveying. But I'm just putting a moniker out there and saying, why don't we call this thing the Solar System Monitoring Network, or the SSN? Catchy 3-letter acronym. But the first thing that you're going to run into as a complication is funding. Who's going to pay for all this? Well, that's going to require significant funding. And if we start with certain big planets and only a few satellites initially, we can spread the costs out over time. But then we have to have a way of justifying the ongoing funding. I'm sure the initial deployment for a large planet like Saturn or Jupiter would be tens of billions. We'll get to a later slide, but the deep space network that is used for communication for deep space probes, we're going to need a whole new network just for monitoring these other deep space probes. And that's going to be, single-digit billions per year for operating costs. We're going to have to design and build these new satellites because let's say we wanted to put some in orbit around Jupiter. Well, if you orbit a satellite around the Earth, if you don't put it into the medium orbit altitude, then they're probably okay. It's easy to build them. If you put them in the medium orbit, you have the Van Allen radiation belts to deal with. And if you put them in orbit around Jupiter, you have even more radiation to worry about. So maybe you can't use exactly the same design as Earth satellites. Maybe you have to do little radiation hardening, or as they call rad hard them, before you can put them in a long-term orbit. Otherwise, they'll self-destruct. Strangely enough, the Juno spacecraft that's currently in orbit around Jupiter, as in the J in Juno, they put a little bit of radiation hardening on it, but some of the instruments aren't rad hardened, and they were expecting it to be toast by now, or the electronics to die, but it hasn't. So that was a surprising thing. Maybe we start with a small quantity of synchronous equatorial orbiting satellites. If you ever look into it, the U.S. National Oceanographic and Atmospheric Administration's long-term weather and climate monitoring system called GOES is a set of geostationary satellites. You've got one over the west coast of the U.S., one over the east coast of the U.S., and they know they're going to run out of fuel because they have to stabilize their orbit, and they know that things break. So whenever they put a GOES satellite up, they also put a replacement satellite in a geostationary orbit not far from there, so that if it fails or runs out of fuel or gets near the end of its life, they just park it over the Pacific Ocean in a parking position there. I'm sure these small nations in the Pacific don't really like that we're using their orbital slots, but they just put them out there. What you gonna do? And they take the one that's the next replacement and move it up in the queue. If you ever watch how they do this, the two satellites are GOES west and GOES east, but then you'll actually see these satellite numberings like GOES 17, and they say, well, GOES 17 is going to be the next GOES west or something like that. And when the previous GOES west, which might have been like GOES 15, starts to get end of life, they'll move it over to a parking orbit and they'll move GOES 17, and it'll change names to be GOES west. If you're going to do this around something the size of Jupiter or Saturn, you're going to need more satellites, and the queue for replacements is going to have to be more than 2 deep. It might have to be 3 or 4 deep because it takes years to get the probes out there. And as I was saying, distances and sizes. Space is big, planets are big, we be slow. You have to synchronize the orbital launch from Earth. You can't wait for like Saturn to come around because it's got a very longer, slower orbit. You wait for the Earth to get in line with Saturn because it goes around the sun faster. So we can do it every 2 years or so, but that may mean that Saturn is not nearer to Earth. We have to may have to wait some multiple of 2 years in order for Saturn to be close enough. And since Saturn has a very much longer orbit, it may be a decade before it'll be close enough again. If you remember the Voyager 1, Voyager 2 flybys, those could do that because all the planets in the solar system were in this convenient lineup, so you could do a gravity assist from Jupiter to Saturn, Saturn to Uranus, Uranus to Neptune. And because the planets Jupiter, Saturn, Uranus, and Neptune are so much larger, you may need more satellites. The field of view of a camera can only go so wide before you start getting distortion. And if you have a large enough view of a big enough planet, you'll get distortion. So that's another reason why you want more cameras, is you can only make the field of view so wide. And you want to cover the poles. And maybe, if you've got large moons around a planet like Jupiter or Saturn, you might actually want to have dedicated satellites that just orbit these major moons. We were speaking of communications and the NASA Deep Space Network. Space is big. The speed of light may sound fast, and the Earth is only a couple of seconds away from the moon, which it's a little delay, but it's okay. When you start to get out to the outer planets, it can take many minutes to hours for a signal to get to the destination, and then for it to respond is maybe milliseconds, thousandths of a second, and now it's got to wait another who knows how many hours for that signal to get back to Earth. So you may want relay satellites, multiple satellites in orbit, so that, let's say, if one of the satellites that's in equatorial orbit sees something while that side is facing away from Earth, instead of waiting 10 hours for the planet to rotate around, you just have a set of relay satellites, and it communicates from one satellite to the other until you get to a satellite that is facing the Earth at that point in time, and you can send a signal back. The geostationary satellites that are in orbit around the Earth for communications with the Deep Space Network actually work that way. So we have the Deep Space Network but we also have orbiters that can relay. For example, the Mars Reconnaissance Orbiter, or MRO, orbits Mars, and whenever Curiosity or Perseverance wants to relay data back up as a rover, they don't communicate directly back with Earth. That would be too energy expensive. So what they'll do is they'll communicate up with MRO, and then MRO will relay back to Earth. So you may have heard of this thing called the NASA Deep Space Network, or the DSN. This is 3 groups of radio satellites, radio antennas and receivers on Earth. There's one station out in California, there's another one in Madrid, Spain, and there's one in Canberra in Australia. 120 degrees separation around the Earth. That way, as the Earth turns, we always have the ability to look at it in any direction in the plane of the solar system. But there's only so many things that the ground stations can look at the same time, because the dish doesn't have a full 120-degree view of the sky. It's got a narrower view of the sky. So as the Earth rotates, it can look at that satellite, and then that satellite, and then that satellite. But there's only so many satellites in the same direction it can look at the same time. Well, on this orbit, we're only going to look at, like Voyager 1. On the next orbit, we'll look at Voyager 2. And then out past Pluto, there's New Horizons. And then you've got Mars Reconnaissance Orbiter, or Curiosity and Perseverance on Mars. And we're putting out these additional long duration probes in deep space, like James Webb Space Telescope, Lucy, Euclid. All these things need the ability to communicate back with Earth using the Deep Space Network. So essentially the DSN is what is known as oversubscribed. I'll catch you on the next orbit, or we'll get the next antenna to point to you. Well, if you threw in this solar system comprehensive network, that would just saturate DSN. This new network would need its own groups of antennas, maybe even more around the Earth, and would also need more people to man it, look at more things at the same time. So maybe multiple antennas at each site, more money. So if you want continuous observing of multiple destinations out in deep space in the solar system, there's a serious long-term investment to keep it all operational. New and risky things are not what commercial entities do. Let's say we deploy some equatorial orbiting satellites, even just 3 of them, to go around Saturn. What's the revenue? Well, initially there won't be any revenue because they're research satellites. That's something the commercial business can't make any money off of, so they can't cover their costs. There are even lunar mining prospectors that want to go and get helium-3, useful in fusion reactors to contain neutrons. And they're saying, how about NASA or the EU pay for whether or not it's commercially viable to mine helium-3 on the moon? Earth has very little helium-3. It all bled off into space. The moon, in its regolith, in its dirt, has a lot of helium-3 trapped in that dirt. Lunar prospecting would be a way to get a lot of helium-3 and then bring it back to Earth, but that costs a lot of money, and let's have NASA do it. And then commercial projects can be funded and operated to do it. If you want to start these new networks of satellites, you got to have government funding, but the government doesn't do these things themselves. They outsource it. So NASA might conceptualize orbital surveillance using equatorial satellites around Saturn. They might even start to design it, but the actual final designs and assembly and building and putting it onto rockets and getting it launched up there, NASA itself doesn't do that. NASA might provide the launch complex facilities and the budget money to cover the cost of the fuel and things like that, but the actual rockets and satellites, they're built by outside contractors like Boeing and Rockwell and SpaceX. So if you want to do this, it'll be under that same approach. But once they're out there, who operates them? You might say NASA does, but then you might be surprised to find that the actual operation of NASA deep space probes is not done by NASA itself. It's a different operations center, part of the Jet Propulsion Laboratory, or JPL, out on the west coast of the US. JPL operates it under a separate budget item from NASA having built them and launched them. And if you're doing science research probes, you might often hear JH or Johns Hopkins University. So that's federal tax dollars funding Johns Hopkins to operate scientific research probes in the solar system. And you get all this data back. How do you archive it so that people have access to it to do interesting things? That's where the Space Telescope Science Institute, or STSCI, they will capture all the data, put it into a database, and then allow people with access, scientific researchers and bumbling idiots like yours truly, to access the data. So you can say, hey, I want to see something from the James Webb Space Telescope. I want to see an image of a moon of Jupiter, and I want to see it from last year using this particular camera. If I know how to enter the search parameters to find that, I can not only see the finished goods, that pretty color picture, I can see all the stack of grayscale images and what filters they use. So I can see the scientific nitty-gritty of the imaging. The US government does have an organization called the National Science Foundation that is afforded a budget with billions of dollars for Earth-based science. That's Earth-based as in we're doing things on Earth that don't directly involve space, but are space associative, like physics. The US National Research Labs like Lawrence Livermore, Lawrence Berkeley, those sorts of places are all funded under the guise of the US National Science Foundation. So whatever means they use for getting these big machines built that do neutrino research, the billions it takes to build that and the millions per year to operate it, however they're justifying that pure science. Maybe you could justify some pure science to discover like practical things around other planets that map to what's happening on Earth. But knowing how NSF gets that initial and recurring funding might be how to get funding for the solar system network. So in summary, Saturn didn't recently add 128 moons. They've been there. They were just observed and then waited for humans to confirm them, but they've been there for a long time. And if we want to get a better understanding of the solar system, we need to have continuous monitoring so we know the complete picture, not just slices, but we can actually see a real-time set of changes as they form, exist, and then dissipate. So the way of doing this is we need to deploy constellations of satellites around different things. And we can start small and grow it out and expand it and update the instruments over time so we spread the costs. It would not only be good for science, it would be good for the global economy. It would employ lots of people with good paying jobs, indirectly employing a lot more people through outsourced products, outsourced services for technology. How about, if people are working somewhere, they're going to need food. If they're traveling, they're going to need travel. If they're traveling, they're going to need hospitality and lodging services. They're going to need rental vehicles. All those are going to need fuels, even if it's electricity, to power it all. So that's basically using the funding to grow how the economy's rolling out to the endpoints. And that's why they say things like every dollar spent with NASA research, if it's big enough, will actually roll out to be $8+ of budgetary revenue coming in. Another thing to think of it is if you have people with decent wages, they contribute their revenue to the GDP, but they also contribute their FICA, their taxes to the economy. So if I don't have a good paying job, I'm not putting in as much to the tax base for the economy. But if I have a good paying job, yes, as a same percentage, I'm going to be paying a total number of dollars more into the economy for taxation. You have the funding, just need to do the programs. Maybe redirect some of those not currently needed military industrial complex projects. The corporations that do that kind of stuff can still get their revenue. They would just be getting their revenue from deep space exploration instead of guns and tanks and airplanes and stuff for wars. Government instantiated projects like this drive economies, plus they advance the scientific understanding of our solar system. So as the saying goes, it's a win-win. And with links. A couple of links associated with the announcement of the 128 additional moons. The University of Iowa is the data operator and presentation announcer for the telescope in Hawaii. So they're the science center for it. And then you have the formal announcement. If you're into the minutia, you can read this. Just a long list of observations of multiple times these 128 moons of Saturn were observed. And then where it started it all was another Anton Petrov video of him talking about finding these new moons. And then if you want to know about, I didn't know about the Canada, France, Hawaii telescope. Well, it's on US soil. Why would Canada and France be operating it? No. They put in lots of funding for it, but it's in Hawaii. And then, how much exploration we've done of Saturn, planet, the rings, the moons, this future Dragonfly NASA probe. And if you want for comparative analysis, I even threw in a link about Earth information and moon information. And then what's this Molniya orbit you speak of? A list of the different possible orbits. Comments? Questions?
I am curious about the revealing and discovery of 128 moons of Saturn. It's done with telescopes and photography.
What actually happened was the Cassini probe, as it orbited Saturn, would see these moons because it was much closer. It would see these objects, and it would take, every time it comes around for an orbit, there's that object again, and they would catalog them and they would plot their orbits. But just having one probe do that does not confirm them. It just puts them in the wait to be confirmed list. So they've got 128 that were recently confirmed. They've got more that have been observed waiting to be confirmed.
Okay.
But since we're not sending another probe to Saturn anytime soon, how do we confirm them? How do we take this to be confirmed list,
right,
confirm them? Well, by using advanced optics, these like shoot lasers to the bottom of the atmosphere and see it ripple, and then using that to counter distortions in the optics, you can take a large telescope on top of a mountain in Hawaii and see those moons, very tiny moon. And so you can actually, over a couple of nights, watch the moons move. So you can better calculate their orbits. Now that you have two different instruments, two different probes, one orbiting Saturn, one Earth base with two different science teams, so everything's on the up and up, you can log all these observations, and then the MPC, the Minor Planet Center, can look over the data and go, okay, I see the data you've given us. And they go through, and it takes, maybe a year plus for each batch of new moons to be confirmed as, okay, are you seeing the same moon twice and calling it two? Or are you seeing a different moon? So they have to actually do computer simulations of all the orbits, of all the things you think you've seen, to confirm, yes, these are unique. They are orbital. They're not like flybys and gone. They're genuinely in orbit, and we've calculated the orbits. So it takes a while. So they won't do them onesies. They'll do a clump of them at a time, and it takes over a year. So ka-chunk, out comes 128.
So, but they're doing this with photographs of Saturn?
They're doing this with mostly infrared, because if these things are not bright, they don't have a high albedo, they may be brighter in the infrared spectrum. So the telescope is optical, but the actual sensor is infrared.
Now, does somebody have to sit and count the dots?
No, they have computers that do that stuff.
Oh, okay. I can't imagine 128 moons by somebody sitting there looking at a photo.
Now, the people do the confirming. I mean, they'll do, some blink detect sampling. That's where you look at a picture from tonight, you look at a picture from last night. Look, the little white dot moved. Yes, we are seeing something that changes from night to night. And then they'll watch it over a long period, and it'll orbit the planet. And then they'll calculate the orbit, the tilt, the elongation of it, the eccentricity, and they'll come up with an orbit and go, yep, it's one new thing. We didn't see the same thing. We didn't see two different things. We saw one thing multiple times. So they'll see them over time, calculate the orbits, confirm them. And you need two different sets of instruments and two different science teams, multiple, periods of observation, and you run all this stuff together, clean it all up, send it into the Minor Planet Center, and they go, oh my God, we got a lot of work to do. And then over a year's time, they'll confirm that they're all unique objects and actually log for official purposes their orbital parameters. Good things take time. Any other comments or questions? Otherwise, I'll stop recording. Okay.